Hi everyone. Next part of our module 4.4. This is, as I told you yesterday, it is a pretty long concept. Transformations. It talks about translations, dilations, reflections. So I had filmed all about translations yesterday, and we had talked about a graph moving up or down or shifting left or right. So now we are going to go into dilations. So dilations, also called stretch or shrink, and a dilation can be vertical or it can be horizontal. So let's look at some of the vertical dilations and what that means. So let's look at this, what it's saying, dilations of linear functions. And the graph of g of x is equal to ax is the graph of f of x is equal to x stretched or compressed vertically. So basically, what is it meaning? That we are multiplying a component, a constant, with either x. All right, so, and that a is either greater than 0 or it is going to be less than 1 but greater than 0. So that tells you how it's going to be either stretched or compressed, okay? So if the absolute value of a is greater than 1, the graph of f of x is stretched vertically away from the x-axis. So you can see that graph, if I say 3x or 4x, so the graph is going to be steeper, and that's basically what stretched vertically away from the x-axis means. And the slope of the graph of a of f of x is steeper than that of the graph of f of x. Okay, so think of it. If I say y is equal to x, or if I say y is equal to 5x. So if you think of it, we know which one is going to go a lot faster and be more steep upwards, and that would be y is equal to 5x. And that's basically what this means. Let's look at the other one. And this one, if 0 is less than absolute value of a, which is less than 1, the graph of f of x is compressed vertically toward the x-axis. So if it is greater than 0, it's less than 1, that means it's a fraction, right? So my absolute value of a here, I'm talking about, will probably be something like 1/2 or 1/4, etc. Okay, so that is a number which is greater than 0, but it's less than 1. So because of that, when we plug in those values, and we're going to see that in a minute, my graph becomes more compressed. So it's like flatter. It's like squishing down something, so it gets flatter. So if you look at this, compared to this, look how steep this is. This is not going to be that steep. All right, so the slope of the graph of a times f of x is less steep than that of the graph of f of x. So that is a vertical dilation of linear functions. Now, just remember that a dilation, as you can see, it stretches or compresses the graph of a function. And we had talked about a vertical dilation just now. And what did we say? That when a linear function f of x is multiplied by a positive constant a, the result a times f of x is a vertical dilation, right? Now let's look at a horizontal dilation, what that is going to be. All right, so when x is multiplied by a positive constant a before a linear function f of x is evaluated, the result f a times x, now this is grouped, see? A times x is a horizontal dilation. So once again, let's look at the difference between the two really quick. Okay, and if I say vertical, In a vertical, when the linear function, what is happening to that one? It is going to be like this. For vertical dilation, we have a times, okay, a times f of x. And then let's look at our horizontal dilation. Okay, when x is multiplied by a positive constant a before a linear function f of x is evaluated, here is the result. For horizontal dilation, we are going to do f of a times x. So look, difference between the two. Okay, once again, vertical is a times f of x. This is vertical dilation. All right, and this is horizontal, where that grouping has happened first. So function, the f of a times x, and this one is a times f of x. So I just wanted you to see the difference between the two. Okay, and then look what it's saying again. If a is greater than 1, in this case, for the horizontal one, what's happening? It is compressed horizontally towards the y-axis. In the other one, it was towards the x-axis. Okay, and in this case, if 0 is less than absolute value of a less than 1, which means it's a fraction, the graph of f of x is stretched horizontally away from the y-axis. So away from the y-axis, as you can see. So let's look at this problem, and we are talking about vertical dilations of linear functions, and describe the dilation in g of x is equal to 2 of x as it relates to the graph of the parent function. So if we know the parent function of the linear functions, okay, what is our parent function once again? Our parent function is, what is a y equal to? Y is equal to x, or x is equal to f of x, right? And that's basically what the parent function is when we are talking about linear functions. So I can also write it like this. We have x is equal to f of x, or f of x is equal to x, right? So the input is equal to the output, and that's what we get, a straight line. And if I had to graph this, I'm just going to show you. Let me use the color black. So we know for y is equal to x, or x is equal to y, as we are talking about this. And if I have my input output values, okay, if x and this is y, let's look what happens. When I have -2, y is -2. When I have 0, y is 0. If I have +2, y is 2. So whatever x is, y is the same thing. And that's what my parent function is for a linear function. So if I'm going to go ahead and I've created a coordinate graph over here, I'm going to go ahead and graph these values once again. So look, 0, 0. If y is, x is -2, y is -2. Here we go. If x is 2, y is 2. So this is my graph of the parent function. Okay, so and so once again, what is y? Y is nothing but what? F of x, right? So here is my graph of the parent function. So which is f of x is equal to x. Now, we are going to create a table with the values which we've been given for this new line that we are supposed to create. And it is saying g of x is equal to 2x. So I'm going to go ahead and put certain values for x. Let's say I give you -2, 0, -2, 0, and 1. And we just said that in the parent function, f of x is exactly the same thing as x because x and y are the same. Okay, so that is why f of x is also going to be -2, 0, and 1. Now let's look at the next thing. It is saying 2 times f of x. So this is going to be 2 times -2, 2 times 0, 2 times 1. And what do I get? When I do 2 times -2, I get -4. 2 times 0 is 0. 2 times 1 is 2. So now what am I doing? I am making my ordered pair with the x and 2 times f of x. So my ordered pairs now, this is -2, -4. I have 0 and 0. I have 1 and I have 2. Right? And so now what I'm going to go ahead and do, I am going to go ahead and graph this. So we can see, let me take a different color. Let's say I use green. And I'm going to go ahead and graph x and g of x. So -2, -4. Here's -2, here is -4. Okay, then I have 0, 0, and then I have 1, 2. I have 1, 2. So now when I connect this, this is what I am going to get. Here's my graph. All right, and you can see that is so much steeper. So the first one, what is my first graph? This graph is my f of x, right? And my second graph is my g of x. G of x. So this is basically what a vertical dilation is. And so we can see that the positive constant a is not grouped with x. It's not grouped with x. So because of that, and we know that 2 is greater than 1. So the graph of f of x is stretched vertically by a factor of a, which is 2 in this case. What is the scaling factor here? The scaling factor is 2. Okay, and so g of x is equal to 2 of x is a vertical stretch of the graph of the parent function. The slope of the graph of g of x is steeper than that of f of x, and you can just see that. If this was 10x, it would be even more steep, right? Because we would have 1 times 10 is 10, 2 times 10 is 20, 3 times 10 is 30. So think about how steep that slope is going to be compared to the original function f of x is equal to x. So it would be way steeper. It would be even steeper than 2x. All right, so now let's talk about this one really quick. It's saying describe the transformation. We are again still on vertical right now. So describe the transformation in g of x is equal to 6 of x as it relates to the graph of the parent function. So the graph of g of x is equal to 6 of x is a is going to be going this way, steeper, right? So this is a vertical stretch. So because it is steeper compared to the parent function, because the parent function is f of x is equal to x, right? And this is like 6 times that. So we know that it is going to go much steeper. So this is, what is this? This is a vertical stretch. This is a vertical stretch. And again, there's no grouping. So that is why this is a vertical stretch. And the slope of the graph, g of x, is steeper than that of the parent function. Now, let's look at a horizontal dilation. Okay, so let's look at this one. Now see how this is grouped together, and that's what makes it a horizontal dilation, because this is grouped together. And now we are going to go ahead and see how this one differs from the other one that we just created. All right, so let's look at this one. As we were just working on this, I've gone ahead and created a table. And then we are always going to obviously plot it. But I've already graphed the parent function, which is f of x is equal to x. Once again, if x is 0, y is 0. If x is 1, y is 1. If x is -2, y is -2. So basically, that's what the parent function is, which I've already graphed over here for a linear function. Now let's look at this one. This is a horizontal dilation, as we just talked about, because now this is grouped. And so we've got to perform that part of the calculation first. Now let me give some values to x. And because I can see that it is 1/4 x, it is between 0 and 1. Okay, so we know that for me to multiply with 1/4, I want to take numbers which I can find are compatible with 4. So when I divide, it's going to be easy for me to simplify. So I can take 4, 8, 16, 20, etc. These kind of numbers, because I can easily divide 4 by 4, 8 by 4, etc. So I'm going to go ahead and take -4. This is -4 as x. I'm going to take 0 and I'm going to take 4. Here are 3 values that I have taken over here. And so now when I do 1/4 x, I'm doing 1/4 times -4. What do I get in this case? I get 4 divided by 4 is 1, and then that has a negative sign. So this gives me -1. I have 1/4 times 0, and anything times 0 is 0. And then I have 1/4 times 4. So what is 4 divided by 4? And both are positive, so I get a +1. Okay, so now that I have my value, f of 1/4 x is going to be -1, 0, and 1. And then what are my ordered pairs for g x and g of x, which is my new graph that I'll be creating, and that gives me -4, -1, -4, -1, 0, 0, 4, 1. So these are 3 of the points that I will be plotting on the graph. So I've already created the graph with the parent function, and this is f of x. And now I'm going to go ahead and graph my g of x. So when I have -4 as x, my y is -1. So this is my y. Okay, here we have 0, 0. And then I have when x is 4, y is 1. So when x is 4, y is 1. So this is where my graph is. And then when I connect, look at the difference of this graph compared to the parent graph. All right, so this one is my g of x. And I can see that the positive constant a is grouped with x. So this is ax. It's grouped together. And a is between what? 0 and 1. And that's why it's a fraction. It is 1/4. And so the graph of f of x is equal to x is stretched horizontally by a factor of 1/a. So this is how horizontally it is going to be stretched by a factor of 1/a or 4. Okay, so g of x is equal to 1/4 of x is a horizontal stretch of the graph of the parent function. The slope of the graph of g of x is less steep. So it's less steep than the parent function f of x. So I just showed you some examples of your dilations, the horizontal and the vertical dilations. So before we wrap up this lesson on just dilations, let me show you the quick comparison between horizontal and the vertical stretch or shrink. So let's look at the horizontal one. In a horizontal one, multiply all the x coordinates or inputs by the same factor a. Whereas in a vertical one, we are multiplying all the y coordinates or outputs by the same factor a. So in one, we are multiplying all the input, which is the horizontal, and in the vertical, we are multiplying all the output by the same factor a. Now, let's look at what happens when a is greater than 1 for horizontal. The transformation is a horizontal shrink, and the graph will shrink towards the y-axis. Whereas when a is greater than 1 in the vertical stretch over here, the dilation, then what is happening? Over there, it's not a shrink anymore. When a is greater than 1, the transformation is a vertical stretch, and the graph will stretch away from the x-axis. Now let's look at what happens when a is greater than 0 and less than 1 for the horizontal stretch. The transformation is going to be a horizontal stretch, and the graph will stretch away from the y-axis. Whereas in the other one, the transformation is going to be a vertical shrink, and the graph will shrink towards the x-axis. And in the first one, where we have the horizontal stretch or shrink, the y-intercept remains the same when the function is transformed by a horizontal shrink or stretch. And then let's look at the other one. In this, the x-intercept remains the same when the function is transformed by a vertical shrink or stretch. And for the horizontal stretch or shrink, the scale factor is 1/a. And whereas for the vertical stretch or shrink, the scale factor is a. So that is the difference between them. But I just showed you how to plot a table, make up a table, and then after that to graph the ordered pairs on a graph next to the parent graph. So you can do that. But this is basically, I just wanted to show you a quick difference between the horizontal and the vertical dilations. And so I am going to conclude the second part of this module. I've done translations in the first part of module 4.4. I've done dilations in the second part of our learning target, as you can see. And then in order to keep the videos not too extended, I'm going to create a third part, and that is going to apply reflections to linear functions. So it is a pretty long lesson, so I prefer to break it down so your comprehension is better. And that concludes everything to do with dilations. Have a great day, everyone.